Very good morning to all. I'm Hui Li from the Institute for Infocom Research. So it's my pleasure to share on task-oriented collaborative question answering. So the brief outline, we shared on motivation, data set, methodology, and findings. Okay, so the collaborative AI project aims to investigate natural human-robot collaboration. Natural human-robot collaboration in a workspace, where the scenario is that a human and robot share a workspace, manipulate related objects, work together, and adjust actions dynamically towards shared goals. There are, however, various open challenges, such as the awareness of the human plans and surrounding, capabilities to understand human speech and actions, provision of feedbacks and interaction with humans, adaptation and refinement of actions to new changes, and other safety, robustness, and trustworthiness issues. So an enabler of effective human-robot collaboration is the effective grounding, which is the construction and maintenance of a shared conception of the operational task. So in the situated human-robot collaboration, although the human and robot are co-present in the shared environment, they have different capabilities in perceiving this shared environment. So humans naturally have a richer representation of the environment, while the robots represent the environment in terms of, say, certain key points. So there is a need to mediate such a representational gap in order to achieve effective grounding. So for our work, we aim to, we formulate this grounding process as a form of question answering with the following main goals for the acknowledgement of existing understanding, correction of wrong facts or concepts, attention to task-related objects, and information about task-related objects and operations. So for instance, referring to the figure here, the human operator could be asking about certain task-related objects. So the robot will be providing certain text and as well as the image reply to guide the operation for the grounding. So the human operator could also be asking about certain task-related operations. In that case, besides the text and image reply, the robot could also provide video reply for the grounding and to guide the user on the next steps. So here are some related works on video question answering. So despite the advancement in the video question answering system, existing task data sets and the solutions are not designed for such a situated human-robot collaboration. So for instance, we have various works with multiple choice and open-end video QA system. So the multiple choice video QA system will be too constrained for such a situated human-robot collaboration. And some open-end answers only provide very short text reply. So these are insufficient for providing clarification nor additional information. There are also limited systems that provide multi-modal spatial and temporal replies. So to the goal of effective grounding through question answering in such a situated human-robot collaboration, we propose the task collaborative question answering, the TCQA, that aims to provide acknowledgement, correction, attention, and information presentation. So formally, this is our TCQA task, where we actually for real-world tasks in such a simulated human-robot collaboration. So we propose this extended answer format. So the setup is that given the query video and the text or speech on certain task-related objects or operations, the system is expected to provide the text answers of answer or instruction, as well as the image indicating the objects that are involved in the operations, as well as a video to guide the user on how to perform the operations. So for this, we collected the TCQA data set. So this is involving simulated teacher-student collaboration of industrial task of this gearbox assembly and this assembly. As shown here, we use this Acne Shaft mounted speech reducer. We've used the collaboration scenarios are designed based on the manual of this gearbox assembly and this assembly. So over here, we use a simulated teacher-student collaboration scenario. So one partner is assumed to be the knowledgeable party, where they have the knowledge of the task to be performed, and the other is the student. They are considered the novice. So for both of them, they can actually freely inquire about the task-related objects and operations via verbal and non-verbal questions and answers. So this data set is rich in instruction expression. So essentially, the instruction expressions are the human instructions and questions. And it's also rich in the task operations. These are the plan and intention-driven hand actions, operation of the objects. So this data set is challenging visually because it comprises the very small parts of a very visually similar looking parts. So it's also challenging in the form that it contains verbal and non-verbal instructions and gestures in order to complete the task. So on top of that, of the instruction, expression, and task operation videos, we also augment the data set in terms of the expression of the questions, the pronouns in the questions. For instance, they could be literal grounding, where there is explicit object parts being used, and also associated grounding, which involve implicit objects references, and also the composed grounding, including both the implicit and explicit objects. We also amend it in terms of the negative scenario, since the natural data set is more skewed towards the positive scenarios. So this is a brief examples of some of the questions asking about, the locations, the number of parts, as well as how to perform the certain operations, where the system is expected to give the text answer and reply, as well as provide the localization, as well as the video to guide the user. So this is a brief breakdown. So almost similar literal grounding as well as composed grounding. So over here, we analyze and benchmark different solutions to the TCQA task. So mainly we have two. We have the state of the art deep learning approach, as well as the hybrid AI approach that Lian was introducing earlier. So let me first share the deep learning solution. So for the deep learning solution, we use one of the state of the art multi-model self-supervised learning framework, which is meant for video understanding and generation. So they have they're pre-trained on large data set, and we adapted the video captioning framework for the text reply, and the video retrieval framework for the video reply. We do this for ease of understanding. We're working on a droid model. And for the hybrid AI model, so typically for deep learning solution, we actually require a large training data set, a large corpus. So in order to overcome this, we also propose our hybrid AI solution, where we use the deep learning network for the front end visual perception, and then the probabilistic reasoning for the grounding. So over here, the front end is driven by the deep learning network. So for the perception, the bottom-up perception on the deep learning deep neural network, we use the faster RTN with ResNet 101 and train it on the Cocoa and fine-tune it for other object and hand detection. We also use the deep convolutional network plus the visual working memory for the hand gesture recognition and pointing direction estimation. And the questions are tokenized and passed based on a certain predefined vocabulary. So coming to the semantic inference for the grounding grounding graph. So as mentioned, we do not need a large data set for the training as compared to the deep learning approach. However, this inference is actually designed based on the common knowledge of the task to be performed. So the domain specific vocabulary have to be provided. So for the semantic inference on the grounding graph, we involves the spatial association between the hand gesture and objects, symbol matching between the vision detections and object in questions, as well as we use direct linking for the literal grounding and indirect linking for the associate and composed grounding. So for the evaluation, we evaluate the text, image, and reply. So for the text, we evaluate the semantic representation for between the predicted and the ground truth answers. For each reply, we actually extract the semantic tuples of this form semantic object and action, and we use F measure. And for the image reply, we also use the F measure, and for the video, we use accuracy. So these are some of the results. So we propose a different evaluation protocol to actually evaluate the robustness under different situations. So for the first one, we have the random split. So the random split is the standard deep learning protocol. So it will work well for the deep learning method where there are large data set. So as expected, we actually see good performance of deep learning method, but it does not fully meet the TCQA scenario. For where the TCQA scenario, we actually want to establish and maintain common ground in novel situation in the collaboration. So once trained on the one task, we want to be easily transferred to some other tasks. So for this, we also come up with several other test splits. So one of it is the split on the explicit and implicit instructions. So the train set will comprise the literal grounding, and the test set will comprise the associated and composed grounding. So this helps to evaluate the reasoning on the multimodal interactions. And also the split on object labels will be that on the novel object labels, how will they perform under such scenarios. And the last one will be the split on environment, where the TCQA scenario is that you want to evaluate how well it works when transferred to novel working environment. So we can see that under the other various splits, the deep learning methods actually falls on the unseen scenarios, while the hybrid AI remains more robust when transferred over to the unseen scenarios. So over here, there are some brief discussion. So as mentioned, the deep learning will require the videos of all the IE and TO. So this there will be risk of combinatory explosion. And under IID, we can achieve strong performance, but it may not be robust to unseen scenarios. So we need the human efforts for the data augmentation for robust performance. On the other hand, for the hybrid AI, we uses the deep learning for the front-end visual perception and the probabilistic reasoning for the back-end. So the prerequisite will be this neural detection and probabilistic front-end rules. There's less effort to prepare the data for training because it's mainly driven by the probabilistic rules. So in the case, it might not achieve the best performance, and there might be increase in programming logic as the task becomes more complex. So here are some examples of the scenario. So you can see that when given certain questions, both the hybrid AI and the deep learning method can actually ground correctly. And these are the reply on these objects which are involved in the operations. Okay, so I'll skip some. So there are also challenging cases where it fails. So particularly towards small parts, like we have all-level indicator and the reader plug, so which are small. So both methods couldn't ground very well. And for this one, so there are various objects along the path of pointing. So the the person is actually pointing along this direction. So there are various objects. So there are referential ambiguities that cause the failure cases. So these are more examples. So coming to the conclusion, so we propose the TCQA task, which aims to investigate question answering for common grounding that provides acknowledgement, correction, attention, and information presentation for such a situated human-robot collaboration. And we propose new tasks, data set, and methods where we investigate different approaches for the task. So there are outstanding works that we are still working on, extension of the TCQA data set, improvement of performance, and handling more complex tasks and reasoning, as well as extension to more interactive QA. So this some of the work by our group, and that's all to my presentation. Thank you.